Ladies and gentlemen, let's continue with lecture 03 of 2016, course in heat transfer, and the textbook we are using is based on the textbook of Cengel and Ghajar. I'm busy with chapter 4 on unsteady heat transfer, and with the previous lecture we've looked at in general where does unsteady heat transfer fit into, what does it mean? It means the temperature is not constant as a function of time. Okay, that is the important thing of unsteady heat transfer or transient heat transfer. That's the first thing that is important so far in this chapter. Then the second thing is we've derived an equation from first principles, equation that in future can be used to predict the temperature as function of time. However, it has a limitation, and a very, very important limitation, and that is that thing of the Biot number. The Biot number, which should be very small, and in theory it will give you an exact solution only when the Biot number is equal to 0. So in practice that never happens. So I've explained to you yesterday that the Biot number is all about the ratio of the conduction heat transfer to the convection heat transfer. So that is the resistance of conduction to convection. Okay. And in general, if this ratio is about 10 or smaller, then the lump system approach will work very well. I want you to go and read specifically on page 239. Underneath the Biot number, there's a very important explanation. So mark it as very important so that you can go and read it again when you prepare for tests and exams. So what it specifically mentioned is this thing that I'm mentioning here about the ratio of the resistance. And what they also say there is that typically if the Biot number is smaller than 0.1, then the error in your temperature predictions or in your time predictions would be approximately less than 15%. So for us as engineers, in many cases, that is fine. The lump system approach, unfortunately, has a very important limitation, and that is whatever the body is, the temperatures everywhere in the body would be the same. That would be the prediction. And that is the reason why this term must be very small for that assumption to be valid. So in general, we've said if we look at the Biot number, to get applications where the Biot number would work well is of course where the Biot number is smaller than 0.1. But sometimes, depending on what I'm asking you, you can start a calculation and it wouldn't be possible for you to calculate the Biot number. Okay, so that can also happen. So you will have to make the assumption that maybe it is, but sometimes it will also be possible to see it's not even going to work. I shouldn't even try the lump system approach. When will that be? It will work well, typically the lump system approach, when the heat transfer coefficient is small. So normally the body is exposed to an environment of natural convection. There's not a fan, it is not moving at a large velocity or anything like that. That's the first thing. The second thing is the characteristic length must be small. So it must be a small geometry and a small object. And the third thing is the thermal conductivity must be very high. So stainless steel, copper, etc. Okay. If we think of a body, typically, that is in an environment with wind, it's big, and maybe the body is from glass or an insulation material with a very low K, then we would immediately know that the lump system approach is not going to work. Okay, so that is very important. Now, something else that I'm going to show to you, which is not in the textbook, which is a critical thing, is the thing about the characteristic length. Because now you've seen this definition of the characteristic length. And you look at this chapter and you say, right, I'm going to get to a problem, and later on, here's a big equation, and in the equation there's the characteristic length, and now I'm going to calculate it like that. So most probably you're going to make an error. Okay. So I'm going to show you something which is very important now that you always should take into consideration. And that is the following. So if we typically look at simple geometries, and with simple geometries, I typically mean the three geometries that we are going to do in this lecture and in the next lecture, and calculated the characteristic length with a lumped system in comparison with later on in the chapter. Then you'll see the following. So I'm going to make a comparison of what would happen if you calculate the characteristic length with this definition of the lumped system to what is actually prescribed in the textbook, and you'll see there's a big difference. So you have to be very careful for that. So one of the first bodies that we're going to look at is a large plane wall. A large plane wall. And a large plane wall would typically be a sheet of material with a very, very long length and the thickness relatively thin. Okay, typically like that, with a width of 2L. And because it is so long, okay, the heat transfer is going to be predominantly in one direction. So it is one-dimensional heat transfer. What is happening here and what is happening there or on the sides is not important. Primarily, we know that the heat transfer is in one direction. Okay, so the thickness is 2L, that is the heat transfer length, and let's suppose the length is equal to T. Okay. If we would now go and calculate the surface area of this large plane wall, then it would typically be this perimeter, which is now 2L plus 2L. Let's make that dimension there Z. So it would be equal to 4L plus 2Z multiplied by T. Okay. That is the surface area through which the heat transfer is going to occur. Do you agree? Remember, we do not look at the heat transfer here and the heat transfer there, because it is a large plane wall. So what happens on the 2 points doesn't matter. It is relatively small in comparison with a big problem. You all happy with that? Did I make a mistake or is it fine? Good. Then, oh, sorry, I forgot. With the beer problem yesterday, a student came and told me that I've made a mistake. There were 3 of them who got another answer, and I did go and check they're correct. So the answer of yesterday's problem with the beer can is 7,008 seconds, which is 116.8 minutes. It looks as if the second part of the problem, where you decrease the temperature to -10, I think that answer is correct. Is that right? Okay, so just take note of that correction. Right, so the volume would be equal to 2L, okay, multiplied by Z, the surface area multiplied by T. Okay. So this characteristic length would then be will then be equal to, if you go and calculate it, 2LZ multiplied by T divided by 4L plus 2 times Z multiplied by T. Okay, something like that. And you can cancel the T's and you can go and write the equation easier, okay, in a more different format. However, and this is now the thing that you have to be careful for, when we get to these applications, and you look carefully, and that is the thing, you have to look carefully with the definition of the Biot number. There, by definition, the characteristic length would be equal to L. It's not that value. Okay. Right. Then, the same is for a long cylinder. So for a long cylinder, like that, this diameter is equal to R0. Okay. And we can choose any length there. T can be 1 meter or 10 meters or 100 meters. It doesn't matter. Okay. Again, the heat transfer is only in the one-dimensional direction. It is not in the axial direction. That heat transfer is negligible or it is insulated. Okay. So for this case, if we now go and calculate the characteristic length, which is equal to the volume divided by the area, then the volume is equal to pi divided by 4d squared multiplied by t. Okay, so that is obviously the diameter. And the diameter is equal to 2 times R0. Okay, so that's the volume. Do you agree? Divided by the surface area, and the surface area is pi d multiplied by t. So if we go and calculate it and write the diameter as a function of radius, then we get R0 divided by 2 is the characteristic length. Okay. However, if you go and look carefully in the equations that follows later and in the derivations, you will see that the characteristic length that you should use is equal to R0. Okay, and the third application would be a sphere. So for a sphere with radius R0, the characteristic length again is equal to the volume divided by the surface area. I'm sorry, I work in diameters normally, not in radius. Okay, so the volume is equal to pi divided by 6 multiplied by diameter to the third, and the surface area is pi multiplied by d squared. And the result is diameter divided by 6. Okay, and this is equal to 2 times R0 divided by 6. So the characteristic length is equal to R0 divided by 3 for a sphere. Okay, however, and this is now this part of your column. However, later on, if you go and look in the fine print, I'm going to keep on calling it the fine print of the equations, then you will see that the characteristic length that you should use is equal to R0. Okay, so why is this important? It is important because, unfortunately, many students make this mistake in the tests and exams. Okay, they remember about the characteristic length, which is equal to the volume divided by the area. However, remember, this is only relevant to the lump system approach. Okay, it is not a general definition. Okay, it is not a general definition. Okay. Later on, you're going to see that is important. So, let's start now with paragraph 4.2 in the textbook. And paragraph 4.2 says it is about transient heat conduction in large plane walls. Large plane walls, okay? LPW, large plane walls, long cylinders, and spheres. So it is 3 geometries which are being used a lot in engineering, and you'll see later on, they can get solutions for these specific geometries. Remember, we introduce this material from very simple, and we go and make it more complex as we go through the chapter. Right, so let's consider again the long plane wall and use some more, make the line longer on your page, because it's very important to remember the dimensions that we're talking of here is long. Okay, and through here, this is insulated and that is insulated, and the result is that the heat transfer rate, as I've previously said, is in one direction only. It's a one-dimensional heat transfer problem. Okay, typically in the x direction. And traditionally, this thickness is called 2L. Okay. It is just because of the mathematics later on that they prefer using 2L. If I could have done it, I would have called it L. Okay, but that is how it was derived, as equal to 2L. Okay, now let's suppose this body is at a temperature Ti, and it has been in an environment where everything is Ti. So if we measure the temperature as function of time, it is all a constant. Then at T equals 0, the environment temperature is changed to T infinite. Okay. Now, let's look at, I just want to make that a little bit larger, so that I've got some points there. So let's look here at different points in this large plane wall. Let's suppose that is point 1 on the surface. That is point 2 there on the center. That's point 3 there. There's point 4 and there's point 5, etc. Okay. So what we would like to do now is, which is different than the lump system approach, is we would like to know at different positions in the body what is the temperature. Okay, so it is a more complex type of solution. We also know that if we look at the temperature as a function of time, for all these different points, that they would be different now. For example, let's suppose this is being cooled. The environment is being cooled. Where would you say would the coolest point be? Point with the lowest temperature, and where will the highest temperature be? From experience, you know, and that is like eating food, okay, is that on the surface it is the coolest, while the temperature is at its highest at the deepest point. So that we know from experience. And if we heat it, we know it's the other way around. That would be the highest temperature and that would be the lowest one. It takes longer before it is being heated to the center, just like a braai of a barbecue with a steak. Okay? You start braaiing it, you can immediately see what is happening on the surface, but on the inside it is not ready yet. It takes a while before the temperature reaches its correct temperature. So the temperatures would typically, for point 1, would do something like that, and for point 2 and point 3 would be on the same line, because it's both on the center line, etc. So we will have different types of temperatures as function of time for different positions in this body. Okay. Now this chapter, or paragraph 4.2, is divided into 3 parts. The large plane wall, the long cylinder, and the sphere. And how it fits together is as follows. So with the long plane wall, with the cylinder, the long cylinder, and the sphere, is that, okay, there's a long derivation that is going to follow. Okay, so while we are busy with this thing, most of you would think that up to now this course is one of my popular ones, or my favorite ones, but through this, most probably you're going to say, no, this is not for me. Okay, but be patient. Okay, so the mathematics is a little bit complex, and we are going to end the lecture also maybe on a point where you do not really understand what is happening, but I will make it more clear with the next lecture and put everything together. But what is important at this stage is that you actually realize where we are going and how things are being put together. So we are going to start with lots of mathematics and a derivation, starting typically with equation 4.10a, and then it goes to equation 4.22, and then there are also very important tables with the results, typically table 4.1, and in it also table 4.2, 4.3, there's a table 4.28, and then there's also 4.33 to 4.35. Something like that. Okay. So this derivation is being done for the large plane wall. But there's a gap here for those two. So we're not going to do that, because it's a little bit boring. In any case, you've passed mathematics, so this is not an exercise in mathematics. Okay. But the results, these results, are all summarized for all 3 the cases very neatly. Okay, so that is how everything is going to fit together in this paragraph. So, it starts by using the energy equation, because what else shall we use? So the energy equation Okay, and the energy equation, almost in its most fundamental form, relevant to us in heat transfer, and that was derived previously in some of the previous chapters and in the previous module for this course, looks like this. Partial d dx of k dt dx plus partial d dy k dt dy plus partial d dz k dt dz plus E gen is equal to rho c partial dt dt. You recognize that equation? Okay. ddx of k dt dx plus ddy of k dt dy plus ddz of k dt dz plus E gen is equal to rho c partial dt dt. This is the heat transfer rate in the x direction, the y direction, and in the z direction. E gen is where you're going to put in energy, like typically electrical energy or a nuclear reaction. Okay. And this term, where previously you've always thrown it away, is becoming the most important term now, because we want to know how this temperature changes as a function of time. So this is the unsteady term. So if we now look at this problem, and remember we've made the assumption that the heat transfer rate is only in one direction. In this direction, it's very long, so this heat transfer is negligible or is insulated, as well as on the other two sides, this side and the other side. There's no heat transfer in that direction. So if that is the case, then we can say that the heat transfer rate in the y direction is 0. The heat transfer rate in the z direction is equal to 0. And fortunately, there's no E gen on the inside. Okay. So the resulting equation looks like that. But another thing that is very important is that this k is dependent on the direction, x, y, or z. That is why it is not on this side of the bracket, so it's not a constant. Excuse me. So when is that important? Well, that is important or relevant if we have a material like a composite material where the thermal conductivity are different in different directions. But to start off, we're not going to work with a complex material like that. The materials that we use normally, the thermal conductivities are the same in all directions. So this k is also constant. And because of that, we can now say that k d2t dx squared is equal to rho c partial dt dt. Take note, this is at this stage not Cp or Cv or anything like that, because we don't know if it is a solid, if it is a gas, or if the process happens at a constant pressure or at a constant volume. So we keep it general at this stage. So let's get all the constants together. Partial d2t dx squared is equal to rho c divided by k partial dt dt. And that is equal to 1 divided by alpha partial dt dt. And that is equation 1. Okay. Now, if you're worried about what is alpha, it is because you just most probably forgot that alpha is just equal to k divided by rho c, and it's called the thermal diffusivity of the material. So it is a material characteristic which is a combination of the thermal conductivity, the density, and the C value. The thermal diffusivity. Let me write it down. Thermal there you go. Okay? So that is the equation that we need to solve for this problem. Now to do that, as you know, if you've got a partial differential equation like that, if you want to solve it, you need boundary conditions. And in this case, you do not only need boundary conditions, you also need an initial condition, because you need to say what happens at t equals 0. Okay. So the boundary conditions I'm going to remove this. Okay, BC is boundary condition 1. Okay, I'm going to use it a lot. BC is boundary condition 1. So, the first boundary condition that we know would be to look at partial dt bx, and that would be for the temperature at point x as a function of time. Okay, now the first thing that we know is that if we look at this body and it cools, remember, T environment on this side and T environment on this side. So the heat transfer rate would be the same in both directions. So in the beginning, the temperature right through the body would look something like that. It would be uniform at T equals 0. Okay, that would be the temperature if we measure it right through. And then at T equals 0, we will have a temperature gradient like that. The heat would start moving out, okay? And then later on it would do that, okay, and then that, and then later on it would start doing something like that. And after a very long time, we will have a temperature like that, right through the body. Do you agree? Now the thing that is very important here is there's a boundary condition, because the gradient at x equals 0, so we call that x equals 0, that point there, there's our x. The gradient there is equal to 0. Do you agree? So where x is equal to 0, the gradient is equal to 0. So to put in the very important things, I'm going to do it like that. Partial dt where x is equal to 0. It's a function of time, dx, and that would be equal to 0. So that is a symmetry boundary condition. Do you all agree with me? Okay. The second boundary condition would be minus k partial dt at point xt. I'm going to explain it just now. That term we can write as minus k partial dt at L T dx is equal to the heat transfer coefficient multiplied by T at L T minus T infinite. Okay. So what do we say here? We say that on the surface of the body, there's convection heat transfer. And the convection heat transfer is equal to that term there. But if you look at it very carefully, you would say, but where's the area? Something is wrong in that term. I'm going to explain it just now. Okay. But the principle is that on the surface, what happens on the surface? On the surface, x is equal to L. Okay, so on the surface, x is equal to L. And on that surface, the conduction heat transfer is equal to the convection heat transfer rate. And the conduction heat transfer rate would typically be minus k multiplied by the area dt dx is equal to the heat transfer coefficient multiplied by the area tw minus t infinite. And you'll see that the two areas cancel. Okay. And if you look at that term, you will see this is actually the heat flux. So it's not the heat transfer rate. And that is actually what we have here. So at the boundary, the conduction heat transfer is equal to the convection heat transfer. On the surface, the temperature, TLT, that is the temperature, and the environment temperature is T infinite. You all agree? No questions? Good. The third thing is we need an initial condition. The initial condition is what happens at a certain time period. So the initial condition that we need to use for temperature Txt is then at T, x, and now at time equals 0. Okay. What happens at time equals 0 for the temperature right through the body is that the temperature is equal to Ti. Okay. Are you all happy with that? Good. So that is the boundary conditions. Now if you look at that equation, the equation with that boundary conditions, then the first thing that you're going to say is, oh, you know, I'm not so sure I'm going to solve it. Well, fortunately, there were other people who have solved it for us. And the approach that they followed is to do something which was very elegant. They said, and something that we're going to use a lot in this course, is they're going to non-dimensionalize the problem. Okay. So non-dimensionalize the problem. And how they're going to do it is firstly with a variable which we call a space variable. And that is equal to an x. And the x is sort of an italics x. Okay. And that x is equal to x divided by L. Okay, so if we look at our sketch, if we look at that definition, and x is equal to 0, then x divided by L must be equal to 0. Okay? If we look at that point there, where x is equal to L, then the non-dimensionalized space variable x, big X is equal to L divided by L is equal to 1. So it means that that variable will always vary between 0 and 1. Okay. The next thing is they've non-dimensionalized the temperature. And that temperature is theta. And that, let's do it like that. Theta, which is a function of xt, and that is then equal to the temperature minus T infinite divided by Ti minus T infinite. Okay. So if you compare this term to the temperature term that we had with the lump system approach, that is equal to e to the minus bt. So that has been written in a format as a non-dimensionalized temperature. Again, if you go and look, you will see that this will always vary between 0 and 1. Cannot have another value. Okay. Then, a non-dimensionalized time, tau, and that is equal to alpha t divided by L square. Okay, actually characteristic length square. Okay, so it can be done in terms of tau, but it can also be done in terms of Fourier number, which is FO. And the Fourier number is typically be equal to alpha t divided by V divided by area square. There are different definitions for it. And then the last one is the Biot number, which we have already done. And the Biot number is equal to h multiplied by characteristic length divided by k. Any questions? Okay, so if we look at this problem and we look at before it was dimensionalized, and we look at what are all the variables that can influence the heat transfer rate. If you go through them very carefully, you would see that they are X, L, T, K, alpha, the heat transfer coefficient, Ti, the temperature as a function of T, and T infinite. So in total, there are 8 variables that can influence this problem. Now Now, after it has been dimensionalized, you'll see that theta, the temperature distribution, will only be a function of the space variable x, the Biot number, and the Fourier number. So from 8 to 3. So 3 variables. Okay. 4 if you also include the temperature theta. Okay, and that was a nice trick because it really simplified many of the challenges that people had to solve this equation with all these boundary conditions. So it means that in future, if we can get a solution for this, then for example, we would say we need the temperature distribution at a certain point, which would be from 0 to 1, maybe at 0.5, at a certain Biot number and a certain Fourier number. And then it would give us the non-dimensionalized temperature distribution. And from the non-dimensionalized temperature distribution, we can get the temperature we want. Okay, or the other way around. So that is the moral of the story that they've tried to achieve. Now, if we look at this approach and we go back to the lumped system approach, it means that the lumped system approach can be written as theta is equal to e to the minus the Biot number multiplied by the Fourier number. Okay, in a very simple format. And all the solutions can actually be plotted theta multiplied as a function of the Biot number multiplied by the Fourier number. And if you plot this on a log scale or a length scale, and this on a linear scale, you get a perfect straight line. Now this was very important for the time before when people didn't have computers, because they didn't have to go through all the calculations. They can just go through a graph after they've calculated that, and they can get the non-dimensionalized temperature very easily. Okay. Now, to solve this equation that I've called equation 1, okay, there are 2 approaches that can be followed. The one is an exact solution where you make use of the separation of variables method, and that is the method that is being used in your textbook, or you can use other solutions and other approximate solutions. There are even graphical solutions for this differential equation, and obviously you can solve it numerically also. So the equation at the end of the day reduces to the non-dimensionalized temperature, which is a function of x and tau, is equal to f, which is a function of x, and g, which is a function of tau. And in this format, f is a function of x only, and g is a function of tau only. And you also then make use of a Fourier series to solve the problem. Now the solution of all the mathematics is in your textbook. I don't have time to work through it, but you should be very familiar with it. You've done it in mathematics. Okay, so you just need to go and take a look at it. But then the result came out, and the result looks like this, and it looks a little bit complicated. It gives the non-dimensionalized temperature as a function of a e to the minus lambda squared tau multiplied by the cos of lambda x, a to the n, lambda to the n, something like that. And together with that, lambda multiplied by tan lambda is equal to the Biot number. So there's not an exact solution for lambda. Okay. Now this would obviously means that there's an infinite solution for the Biot number, because the tan function, every pi, you'll have the same, there's a solution for it. Do you remember? It's the tan function. So there's an infinite number of solutions for the Biot number, or for lambda. So if the Biot number is given, then you need to get lambda, but you'll see there are many solutions for it. Okay? For that reason, you need to use the many solutions. So it looks very complicated, but be patient. Then this is called, I hope you remember, the characteristic equation, or the eigenfunction. Do you remember? And it has, the roots are called the characteristic values or the eigenvalues. Okay, now the result of all this is that the solution can be written as theta is equal to the sum of n equal 1 to infinite of an e to the minus lambda n square multiplied by tau multiplied by the cos of lambda n tau, where the constants an is equal to 4 times the sin of lambda n divided by 2 times lambda n plus the sin of 2 times lambda n. Okay, looks very complicated. Do you agree? Yes. Okay. Now remember, if we just go back to this, the schematic of what is happening in paragraph 4.2. What we've done now is we've derived a solution for the large plane wall, and that is the solution. The one for the cylinder and the sphere is not given in the textbook. You can get it somewhere else in literature if you're interested. But the results are then summarized in a table and in graphs. Okay. And with the next lecture, I'm going to go in detail in these results, and with examples, I'm going to show you how they are being applied. Ladies and gentlemen, any questions? If not, oh, there's a question in terms of the work. If we,
why cos lambda tau in the first one and cos lambda tau in the second?
Sorry, adjusted.
Why cos lambda pi in the first one and cos lambda tau in the second?
Why is it cos lambda tau? Do you mean here?
Yeah. Whereas in the previous one it's cos lambda pi.
Oh, right. Sorry. It's most probably, okay. Something that you're going to discover in this course is there's a difference between what I say, mean, and write. And sometimes you have to use your judgment in sorting it out. So I think if I look correctly, it is cos lambda tau. So in terms of what I've got here, I've written this down correctly. So this one from this one to that one to which one? Oh, that one. Oh, sorry, I see now. Yeah. Let me see. It should be tau. Okay, so it should be tau. And then this actually shouldn't be n's. You can actually take those n's out. The n's only come in here with a solution. Okay? Right. There's another question, ladies and gentlemen. Shh. Sorry, with the? Yes. Should
it not be tx0, not t0?
Should it not be tx0 and not t? Yes. Okay. Sorry. This is also an error. So this should be tx like that. Okay. Great. Any more questions? Nothing, ladies and gentlemen. Thank you very much, and I hope I'll see you with the next lecture.